All right. Thanks for the invitation to speak. All right. So I guess earlier today, Gloria Pan talked about this work of Berger-Colmez about interpreting SEM theory, like this description in terms of local analytic vectors, and everything was sort of happening in characteristic zero. So today I want to kind of describe something which aims to generalize this to mixed characteristic, and I'll explain what this means. And this is work in progress, and also aims to generalize, so not everything is perfect. But I hope to spark some of your curiosity about this. And I was sort of led to thinking about this because both of this kind of work of Bakloubi about like this SEM theory, SEM operator, which makes sense in characteristic P, and this on the one hand, and in the other hand, this like work of Berger and Rosenstagen and about these local analytic vectors in characteristic P. So that's how I was led to thinking and believing that there may be something kind of interesting to say about this. And also, I should say that this work of Berger-Colmez was later kind of used by Louis Pan and Rodriguez Camargo in this study of completed cohomology, or at the very least, like the ideas from there. So I hope maybe this can also lead to some interesting ideas. All right, so let me begin. And I want to describe this kind of theory of Berger-Colmez a little bit differently, to say some things would relate to what Louis said, but not exactly the same. SEM theory à la Berger-Colmez. And I was kind of happy about this wordplay. There's one thing you enjoy about this talk, I hope, about this, because you can use it. Okay, so right. So P will be a prime, and K is a finite extension of Q. And I'm going to have some extension K infinity over K with the gamma of gamma, which is a p-adic group of dimension D. So that kind of like in Lewis talk, but with slightly different notation. And as pointed out, that means that the completion of this extension is perfective. And also let me set G of the absolute gamma group of K and H of the gamma group of K infinity. So that gamma is the quotient of G by H. All right, and let me also set gamma 0 side gamma to be an open, uniform, and at least. Sorry. This is like this kind of sample for which we kind of can relate it to the algebra.
Sorry, is P at least 2?
Is P at least 2?
D.
D.
Yeah, it's equivalence.
I think it's expired that you would take the hammer 5 instead of the extension.
Right, so let's say infinitely high. Thanks. Is that good? Yes? Okay. Thanks. Right. Okay. And okay, we have this subgroup here, which is the sort of like subgroup small enough to have like sort of coordinates. And we set gamma n to be like the p to the nth powers of gamma 0. What? So that's the setting. All right. And so I'm going to have this category, which is gamma semilinear representations with coefficients in K infinity hat. Let's say finite dimensional. And all right, so for example, if V is a representation, it's a p-adic representation, then a classical example would be to tensor with CP and take H invariants. Okay, so here's what the theory of Berger-Colmez says. It kind of has similar parts. So first of all, there's descent to local analytic vectors. Descent. All right, so it says that if W belongs to this category, an object of this category, then the natural mode extending from local analytic vectors is an isomorphism. One has descent to locally analytic vectors, so you can understand such representations using the locally analytic vectors. The second result that I want to state, but so that's the vanishing of the higher locally analytic vectors. So I guess this result should be attributed to Ruepan. Although Ruepan says in his paper, it's obviously something like that. It's clearly already in the paper of Berger-Colmez. So it's funny that I'm putting this here and this something here, but I good. I want to think about this this kind of result is also like part of this theory. All right, and it says that sort of for the same type of W, the higher locally analytic vectors vanish. So I guess the locally analytic vectors are sort of a locally exact, left exact pointer, not exactly explaining what's the category. It should be like some sort of solid category. I think to get exactly the correct statement, this category that was introduced by Rodriguez, Jacinto, and Rodriguez Camargo. And the statement is that the higher locally analytic vectors are zero. Again, for W in the same category. The third statement is the description of the locally analytic vectors inside of K infinity, inside of the condition. So there's a few ways to say this. But basically, after extending to CP, so basically we can consider the gamma n analytic vectors. So analytic for like some specific open subgroup of the kind I wrote here. And the statement is that this is isomorphic to like some sort of Banach space on d-1 variables. So d is the dimension of gamma. So I'll give some more specific examples in a second. So the local analytic vectors themselves are like some sort of like a sort of direct limit over these higher denominators.
Can you just ask?
Yep.
In this graph, the gamma, are they finite dimensional over?
Yeah, finite dimension. Sorry, I said it, but didn't write it. Thank you. Other questions? Nice. So finally, the cell operator. So this was introduced in Lewis talk. So let me remind you. So there exists some element inside the LP extension, the CP extension of the Lie algebra of gamma, non-zero, and unique up to scale. Such that it kills the local analytic vectors. So there's this element which kills the local analytic vectors, and therefore, if you have some sort of W local analytic as above, it acts linearly on its extension by scalars to CP. What? So these are the statements. Are there any questions?
In 3, what are you tensoring over?
Sorry?
In the third point, what is the tensor pod?
Right. Yeah, that's a good point. So I just mean like the fixed points, like
I think.
sorry. Oh, you mean this one?
No, the one you were.
Oh, you mean this one?
Yeah.
Right. So it's like the smooth like the gamma and fixed point.
Is this tensor completed or
Excuse me?
the tensor completed?
This tensor is I think completed. Yes. Thank you. Yes. Okay. Right. So how can we think of this? So I'd like to have to. I'm not sure how am I doing in time. What? So I'd like to give a few remarks. Okay. So there's a relation between like 3 and 4. So one can think of of 3 as saying that like really this tensor product on the left sort of isomorphic to this manner thing in B variables, except that this operator theta is like killing the diff variable. So in fact, one can think of this ring as like the ring of sort of analytic functions from gamma n to CP with theta acting by 0. So this is the so I guess what I want to say is like the missing variable has to do with the canonical differential equation theta equals to 0. So that's related to things that Ruepan said. Sort of maybe it's worth remarking that this came up in Paul's talk. So when he was considering this like W locally analytic vectors and these like Cauchy-Riemann equations, these Cauchy-Riemann equations exactly have to do with the other d-1 variables. These are the sort of other things in the Lie algebra which are not the same operator. These are the ones that like these dimensions have to do exactly with these like analytic dimension, like these Cauchy-Riemann equations coming up in his talk. So there's a relationship between these things. Okay, so that's one thing I wanted to say. And this leads on to like all the work on completed cohomology, this like idea of the canonical differential equation and so on. And the other thing I wanted to remark is about part two. So part two sort of implies that you can compute a cohomology with locally analytic vectors. And hence, we have algebra cohomology. So there's like sort of a spectral, like you can try to take cohomology in two steps by first taking locally analytic vectors, and then like sort of the fixed points, and then this kind of says that the local analytic vectors is exact, so you get this kind of isomorphism. Right, so this also uses this like formalism of solid representations that I mentioned. I think it's Jacinto and it's Camargo. Okay, so I can give an example. Okay. So here's an example. Right. So in the cyclotomic case, what happens when we have that the local analytic vectors of the completion just gives back the smooth vectors. And this is classical sense theory. So for example, so if V was without cohomology of like some proper smooth thing, maybe some N, then we will get that, then we would have like this kind of usual construction I mentioned before. And the eigenvalues, the Sen operator would be the negatives of the Hodge numbers. So that's the familiar thing. Right. Okay. And maybe it's also we're saying something about the Rubin-Tate case. So in the Rubin-Tate case, let's say that we have the Rubin-Tate extension for E over QP, a finite extension. So consider Rubin-Tate for E. What we would have is like some sort of, you would have like, you would get these like co-limits over like, yeah, maybe I need to write something like this. You would get like these variables indexed by the embeddings, which are not the identity embedding, from E to E bar. And what would happen is that inside the CP tensor the Lie algebra, like the Lie algebra would sort of be identified with E. So this would be the same as that over QP. And this would be isomorphic to product over the embeddings. And sorry. And what would happen would be that theta, like the Sen operator here, would correspond to the thing which is 1 in the identity embedding and 0 elsewhere. So I think maybe Matt said something like this in Louis Pan's talk. But this is what happens.
Yeah, and this first example should be the negatives of the I such that Hij is not 0.
Sorry?
Should it be the negatives of the I such that Hij is not 0?
Yeah. Yeah, sorry. Yes. So Yes. Okay, so these elements are sort of the periods for the twists of the Lubin-Tate character. So they're sort of like no period for the Lubin-Tate character in CP, but there are for like the twist by the embedded. So these are the elements that you get here. Okay. Any questions?
So E is equal to K in this part two, or
No.
what is E?
So E is like you consider like sort of I mean you consider sort of the Lubin-Tate extension for E.
Before you had K, so what's the difference? I mean,
So before you had like the cyclotomic extensions like the Lubin-Tate extension for
I
QP.
think the question is just at the very beginning, there's a K over QP. And maybe that K over P is become E over.
so maybe you could explain what is E?
Yeah, maybe let's take E equals to K. So thanks. All right. Okay. So what I wanted to say next. Okay, so a lot of this can be generalized to like some more general setting. So as some of you may know, there are these trace maps from the completion of the cyclotomic extension to these fields where you add the p-adic photounity. And these are these sort of decompleting maps. And they were constructed by Tate. So you can construct such decompleting maps in other situations, for example, where you have this like these example that came up in the previous talk, in one of the previous talks today, that like, I mean, you had these like sort of extensions of this form, and like for this kind of perfectory terms, and you also have like these decompleting maps in this situation, and a lot of the kind of results you can also like kind of generalize the situation like that. So let's say that. So I don't want to be exactly. So I want to be vague on purpose about this, but actually this will come up in some of the examples. So let's say that like a ring lambda with group gamma is Tate same, is Tate same. And if we can write some sort of triangle, so on the one hand, we have this like sort of decompleting maps for some lambda 0, and on the other hand, we have this like sort of up to upper finite null extension here, and like some sort of locally analytic covering here that I don't want to make precise with the string, locally analytic covering. But if we can write some sort of triangle like this, then the results kind of also hold for lambda. So there will be other situations where like, or at least 1 and 2 would hold. So, so 1 and 2 would hold if in the Tate same situation.
So the thing you call lambda 0 is sort of like a lambda 0 common infinity.
Right. Yeah.
That's a
Yeah. So right. So it could be something that like lambda 0 comma infinity is this thing, and lambda 0 n is this thing, and then you don't literally have to be this example. You can be this example up to something like maybe you do like some extension by ZP and then you can descend. Actually, this is sometimes important and comes up in some of the examples. So I suppose that you can show that 1 and 2 still hold, and this is I guess this was shown by Rodriguez Camargo and in a paper of mine roughly at the same time. So this is something you can do. And okay, so the example would be like, right, so the example would be, of course, what we've seen, it would be an example like this. There aren't like these maps from K infinity height in general, but they are from the cyclotomic extension, and we can sort of relate it and still deduce 1 and 2. All right, any questions? Okay. Right. Okay, so locally analytic vectors mixed characteristic. Okay, so how does this even make sense? So let's say that gamma is again as before, but not necessarily just a p-adic Lie group. And let's say that B is a QP Banach space. We have gamma acting in B, and maybe there's like some unitary condition or continuity. And now we have, as before, these like gamma 0 and gamma n's. And let's say that we have this homeomorphism from gamma n to ZP to the D. Okay, then let's recall what are the analytic vectors. So the analytic vectors, they are these elements of B, such that G of X is the sum of CG to the n, Xn, maybe like some sort of vector n, because we have like several dimensions at once. So we like need maybe to raise these to different powers for different things. And the condition is that Xn goes to 0. So the valuation goes to infinity. So if we have, that's the kind of definition for gamma n analytic vectors, and the locally analytic vectors would be the union over these for different things. So now the thing is like, this sort of is not going to work when B is only like some sort of Banach space in mixed characteristic. So the thing is like that. First of all, as we take smaller and smaller gamma n, this thing is maybe going to be divisible by P. So there's no chance for like things to be analytic. And also like you won't really have good Taylor expansions because you'll have to divide by things divisible by P. So this has no chance of work in mixed characters. But it turns out there's a way to make this work. So there is a way to make this work. With binomial expansions. Maybe Mahler expansions. This kind of observed by different people in different contexts. independently. So there's Berger, Rosenstraßen, Lothar, Johansen Newton, and also Carter and Berger. All kinds of uses this idea relatively recently in different works. The idea is just to use Mahler expansions. Okay. So recall there's this like classical theorem of Mahler about continuous functions. So I think it was mentioned before in the talk before. Or maybe the analytic version was mentioned. So these are these functions. So basically every continuous function has a binomial expansion where the a and let me write it like this, where the valuation goes to infinity. So all the continuous functions look like this. And then there's sort of the theorem of Hermes that says that the locally analytic functions inside of these sets such that there exists some alpha and beta such that the valuation goes to infinity at least linearly. Right. So the idea is like we can still make everything work in mixed characteristic if we use basically generalize these things. So now let's so now now I want to let B be an arbitrary. Arbitrary Banach ring. So that means we're not assuming QP, that it's a QP algebra. So what I mean by this, really is that like B is some sort of Tate ring, that it has like some sort of valuation that it's induced by one element, and maybe that it's like a ZP algebra. So it's a ZP Tate algebra. I mean, it's a ZP algebra, which is the Tate ring. So that's all I want to assume. And then it turns out that the theorem of Mahler just like works the same. So the theorem is like so kind of first result, sort of already proved by Berger and Rosenstraßen more or less, but maybe not in this generality, but fine. I mean, same description as in Mahler's theorem. With the coefficients in B. So this kind of works the same. And then we can replace the theorem of Hermes. We can replace the theorem as a definition of the local analytic vectors. And then sort of with binomial expansion, we have local analytic vectors in mixed characteristics. Right, so So there's that. So let me kind of spell it out in words, like the sort of local analytic vectors now will be like these elements in V, such that their Maller expansion decreases, like the valuation increases at least linearly.
Can you differentiate these?
Right, so can I differentiate this? So it's not, so let me make it this as a math because it is important. Thanks for the question. Maybe I only have to erase this. Right, so unfortunately, there is no obvious action. Of the linear. Rather, what is sort of what happens is that kind of these kind of functions are the ones that when you apply d over dx, they sort of like decrease I by 1. But we don't have them anymore. But rather, like if you consider these functions as well, instead, they have the property that, well, maybe I could write that. Right, but you no longer have them. But these binomial expansions have the property that if you apply a discrete derivative, you do decrease I by 1. So somehow these still like this is like the operator which takes f of x to f of x plus 1 minus f of x. And then you can try to develop much of the theory using this like discrete derivatives, and a lot of it works like this. So really the Maller expansion is like kind of saying instead of using like derivatives, use discrete derivatives, which on the one hand works, but on the other hand it's not always so fun because you don't have the Leibniz rule, for example.
Maybe this good.
Right?
Just in the case where you literally just get set p.
In the case where?
Just d equal to 1. Just just
Oh, yes.
just continue for set p. Like the dual of this is what people call like the Poisson algebra of p, and maybe just to say that that's the natural action, like the reciprocal action of set p. So just the way you write the Poisson algebra as a power series because of that.
If I understand correctly the remark, then I think yes. Like the sort of, if you now consider like something like local analytic vectors, then this discrete derivative operator becomes something like a gamma minus 1. Maybe that's your remark.
Yes,
yes thank you. Yes, exactly. You can't see the minus. It was here. Okay. All right. Okay. So let's continue. And now that we have the setup, let's start saying interesting things, maybe. So we have this kind of nice example. So let's say that k is equal to qp, and k infinity is the cyclotomic extension. And now the kind of thing we can consider is not the local analytic vectors in k infinity hat, but rather in the tilt of k infinity hat, the completion of k infinity. So what happens is that this tilt is isomorphic to this unit. So we take fp and we add this one variable with p to the nth roots, and with the adequately complete. We're going to put an underline because it's like a reduced thing. And what happens is that ZP star acts on this because it acts before taking the tilt, because it's the Galois group of the cyclotomic extension. And actually, so let's write gamma for this. And this action, we've already seen it in Rodriguez Camargo. So this is the action which takes the variable to 1 plus t to the a minus 1. And you can ask, like, what are the locally analytic vectors inside here? So, for example, is T a locally analytic vector? Like, maybe it is because you have this like nice expression. And it is. In fact, what you can kind of show is maybe some sort of exercise is that the union, without taking the completion, is in fact locally analytic inside. Whoops. Berger-Colmez, they show that in fact this is an equality. So this like scary, the p-adic completion is undone by taking local analytic vectors. More or less in a similar way that when we took a local analytic, like when we took the completion of K-infinity and we took the local analytic vectors, we just undid the completion. So there's like some analogous behavior, even though there's maybe no action over there. Right.
So are you taking now local analytic versus the characteristic B?
Yes.
Will you maybe define them?
Excuse me?
Will you maybe define them?
On the bottom.
Did I define them?
Yeah, on the bottom.
Right. So I guess it's this one. But basically, you take the same definition. You just use the manner. You use the theorem of Amiss as a definition.
But this is the functions.
Excuse me?
This is the functions.
These are the functions, and then yes, right. So the local, the local analytic vectors are these vectors whose orbit map is behaves like local analytic. Thank you. Yes.
So Berger and Rosenstein, they introduced the super holder.
Right. That's how I call it local analytic, but it's their super whole.
Right. It's the same, yeah.
Yes. It's yes.
Can I swap the LA and the flat? Is it true? If I take
Right, so that's a good question. So, for example, so I don't think it's quite as simple. But for example, something you can show is that if you have like some sort of any k infinity over k, same setup. What you can show is that if you have an element in the tilt whose sharp is a smooth element, then it has to be local analytic. Like I count, in a sense, like the smooth elements are like tilted to local analytic vectors, even though like doesn't really make sense to talk about the tilt of an element, but like yeah, so that would be kind of a proof of this, right? Because I guess this T is kind of its sharp is like a root of unity minus 1, so it's smooth elements, so sort of the smooth elements inside K infinity, they somehow like sort of become these like actual variables which are locally analytic, but no longer smooth. Right. Another question?
Well, what happens if you start from a K infinity where you start from a p-adic group from dimension bigger than 1?
If I start with dimension bigger than 1.
Yeah, if you don't have a cyclotomic expression, but something attached
Right.
to a group of dimensions bigger
Right.
than 1, you still have the K. You have the same equation.
That's what I'm going to talk about, I hope. So hopefully I will answer your question. So the question was, I think, what happens when the dimension is larger in this situation. Yeah, thanks. So I'm gonna talk about this now. Okay. Not exactly now, but in a few minutes. All right. So if I had better board work, I would have on the board these like four parts of the theory of Berger-Colmez, but since I don't have it, you will hopefully be recalled that what I'm going to write now. All right. Right, so some results and then hopefully some applications. So basically, so now we're going to have that B is Banach, and this B gamma pair is Tate-Sim. Everything makes sense in sort of mixed, like you don't need to assume B is QP Banach or anything, so everything still makes sense. And the key example is this K infinity hat tilt. G. Okay, so then we still have descent. So if W is the corresponding thing here, representation, semi-linear representation with coefficients in B and maybe like finite dimensional and so on, then the natural map. So there's a descent to locally analytic vectors in the same way as before. So this will still help. Okay. Part two. So we still have the vanishing of these higher local analytic vectors. So basically, this to 0 for I greater than 0 in the same way as before. So again, this means that we can compute cohomology in the local analytic vectors, but maybe we can no longer relate it to the Lie algebra action because there is no Lie algebra action so far. And let's talk about the other two parts. This is also I have to say that this is where the work is most in progress. So this was the part about the D minus one dimensional ball and about the semi-period. Okay, so so let me say this in the case of K infinity. So I only kind of said what is like the local analytic vectors index characteristic. I kind of didn't define like sort of gamma n analytic vectors, and also I'm using Mahler expansion, so it's not exactly the same. So let's just say that. So let's just say that lambda analytic vectors means that the valuation of the coefficients appearing are increasing by at least p to the lambda n plus u for some u. So this is like the alpha and beta from before. Not exactly clear why I'm switching notation, but I want to use like sort of this because it will be nicer in the normalization. Then the description of analytic elements is as follows. So the claim is that we have this sort of isomorphism here of the lambda analytic vectors in the tilt. So it can't really be the same thing as before. Like it wouldn't really make sense that it would be like this state algebra, but instead what it is, it's like these kind of like sort of omega to the minus lambda n times binomial coefficients. So sort of the kind of ring with so let me explain. So this is a pseudo uniformizer. Maybe like some normalization of the exact evaluation is required. And like here, we're considering the ring instead of power series in the variables, we consider like binomial expansions in the d-1 variables. So this is the kind of ring that we get, which still makes sense in mixed characters. So this is some normalization, which is like some sort of condition on like how large this thing is allowed to be, like the requirements is of size at most one. And I didn't explain over what the tensor product is. So this thing here is over like some m depending on lambda, or this field here, which is some sort of ek, ek infinity, where this is the field of norms. So instead of getting smooth vectors, you get like field of norms. So that's the kind of statement that you have instead. And again, d is the dimension of ground. So we still get this like vanishing of one dimension, but it now appears in this strange form. Right?
You need some completion for the tensor product.
Yeah, sorry. Thank you.
What's this completion?
Sorry?
And what is this completion?
Yeah, that's a good point. Maybe we can. I want to say maybe let's talk about this afterwards, because I for sure am not going to be able to think clearly about this now.
There is solid tensor product.
Sorry?
It says we could take the solid tensor product.
Yeah. That's always the answer.
I mean, like, this is like a tight algebra, so everything is just a Banach algebra, so it's just a completed for the p-adic notation.
Yeah, that's a solid strategy for dealing with them. Okay. Okay, I really hope I have enough time. Okay, this all right. And finally, we sort of do have, well, in one sense, we have, this is the part I'm most unhappy about, but we sort of do have a set operator-ish, more or less. So it's in the following sense, like there is this discrete derivative operator such that in the thing before, we get an isomorphism with CP flat with the sort of d variables with delta equals to 0. So, and here there's the corresponding thing, so omega to the minus something. So basically what we're saying is like now, instead of having this derivative killing the powers of x to the I have this discrete derivative operator which sort of kills the binomial expansions like in xd over I. And it's also like canonical or non-zero. And it's basically some sort of sum of like the gi minus 1 for the different gi's if you pick
It should be killing the other ones, right?
it should be killing the other one. Yeah, sorry, I think I mixed also before. Yeah, thank you. All right. Thanks. Yeah. All right. Okay. So we have this thing. So probably there's much more insight to be gained about this, but this is what I want to say for now. But I do want to finish with something, some application, not of the same operator part, but of the other parts. Okay, so all right.
having trouble parsing the sentence that is written up there. Is the claim that these are locally analytic vectors? Sorry, is that what you're saying? These are the
I'm saying like there's some sort of canonical operator. I'm no longer like, I mean, it's like, it's no longer gonna be true that it kills the local analytic vectors because like this dimension of the field of norms is not smooth anymore, so it's not gonna kill. Like, so that's why I also kind of prepared this in the last minute, so. Yeah, so that's why I'm not claiming that, but it does like come up in like some sort of similar argument before that there's like a canonical operator which gives this isomorphism. And it's like sort of in the direction of the field of norms in the same like way that like sort of the Sen operator is in the cyclotomic direction. It's just no longer true that it's smooth. So yeah, so that's why I'm slightly careful about it. Okay. Let me just kind of conclude. Sorry that I don't have a better answer. Okay, let me just kind of conclude with like some kind of thing about these like rings of coefficients in p-adic theory. So I'll have to be a little quick about this, but basically, there's this kind of famous picture of either like the spar of sort of A inf or the spar of ZP W1XT. And all the kind of phi modules and figure modules and all of these things, they kind of live on this space. Maybe the decompleted version is something over here, and the non-completed version is something over here. And what does this picture mean? Well, this is where P is equal to 0, and this is where T is equal to 0, or maybe some var pi is equal to 0. So really like, I'm sort of painting two pictures, one on top of the other, either for this one and this one. And here we have this sort of kind of radius function with infinity here and 0 here. So the radius function is kind of saying how large T over this var pi is compared to P. So it would be like sort of this function, or maybe the other function. This or this, depending on which space. And then you have sort of inside these y, which is this star of A inf, but remove where P and var pi are 0. And one version with ZP W1. Okay. So basically what I'm trying to say is that I think it's been like, oh, I shouldn't have erased this. Okay. So it's basically, it's been a while where people like considered like locally analytic vectors where P is not 0. So away from where P is 0, you get these like QP-Banach algebras. And then a lot of people like consider the local analytic vectors there. But I guess my point is that also sort of the local analytic vectors kind of, you can work them out and make sense of them for P equals 0 and get some familiar construction. So I guess what I want to say is that you have this thing here, like this is sort of K infinity half till 44. So this is like sort of the residue field at P equals to 0 for the large one, and then you have a version for the small one. And then you have these familiar ones, so like these ring of functions, or like some sort of pizza slice from P. So like sort of the functions where the radius is between 0 and R. Y tilde, a similar incompleted one. And finally, you also have this this p-adic completion, which is the completion at p equal to 0. And similarly, you have a similarly defined one here. Right? So these are like all kind of familiar things that come up in 5-year module theory and all of these things. Maybe somehow in the theory, like in some sense, these are kind of maybe ad hoc. It's kind of the same issue about like the roboring in the previous talk, which its appearance is kind of strange. Well, these are maybe kind of more natural. And I guess the theorem is that if you take something in the left-hand side and you take its local analytic vectors, then you get sort of the right side after inverting for gains in all of these cases. So these are kind of a Banach flavor. This is really like the theorem of Berger-Rosenstein. There's like just kind of a different proof with our methods for it. And this is like sort of a Fréchet example. So this is like some sort of inverse limit or like some sort of Banach rings in like mixed characteristic. And when you take the so basically, I guess like what I'm trying to illustrate is that like all of these like small period rings, they're always like you can sort of canonically get them by taking local analytic vectors of the large. So basically the kind of idea is even next to p equals to 0, all these like kind of ad hoc constructions, at least in some sense, they are like actually natural constructions in terms of local analytic vectors. And in this way, like maybe you can hope to generalize them also to other groups beyond the cyclotomic case.
But except that you have a union of phi minus n of the right hand side.
Excuse me?
You don't have the right hand side, you have the union of phi minus n of the right hand side.
Yes, this is true. Yes. So I mean up to the full.
Can take analytic for some radius, and then you can actually recover some of the actual right-hand side. Right.
Right. Yes. If you take, yes. Thank you.
What did you say?
The comment was that if you take analytic of some fixed, if you require like some strong analyticity of some fixed radius, then you can actually get the right-hand side. As a phrase that you want to locally analytic. I can say something about the proof, but I think maybe I'm out of time. So.